Continue with the third part of the sequential circuit is counter. Basically, what is meaning of counter? Counter is a digital circuit, or it is a one kind of system in which we are going to count or actual number of events. For example, before entered into Mahalakshmi Mandir, there is one electronic device. In that, one by one person is sent inside the temple. That machine is works as an counter, in which how many persons are visited for the temple. In this way, the counter are used to actually count the actual event occurred in that entire time period. So a digital counter is a set of flip-flops. So in which way these counters are implemented? Yes, digital counter is a set of flip-flops whose output is changed in response to applied clock pulses. This is the first basic concept of the counter. The second, flip-flops are interconnected such a manner the state, or we can say output, at any time instant is the binary equivalent, and which is equal to total number of clock pulses. Well, this concept or these definitions are clear when we are going to study what is the exact operation of the counters. I will explain. So these counters are two types. The first one is asynchronous counter and synchronous counters. As per our part of sequential circuit, basically sequential circuit are two types, asynchronous and synchronous. What is meaning of asynchronous? When the circuit doesn't require any clock. In the same way, same fashion, in this type of counter, flip-flops are connected in such a way that output of first flip-flop is acts as a clock to the second, and output of second flip-flop is acts as a clock to the third one, and so on. This is called as asynchronous counter. Okay, what is a synchronous counter? In this type of counter, there is no connection between output of first flip-flop and clock input to the next flip-flop. Then second point of comparison, all flip-flops are clocked simultaneously. Are not clocked simultaneously. But in synchronous counters, all flip-flops are clocked simultaneously. This is a major difference between the asynchronous and synchronous counters. Design and implementation is very easy, where synchronous counters for design and implementation are a little bit complex one. Okay. Next, in asynchronous counter, due to not all flip-flops are not clocked simultaneously, the operation speed is lower one. But in the synchronous counter, due to all flip-flops are clocked simultaneously, the operation speed is higher one. Okay, so the counting will be up counting or down counting. What is meaning of a counter? A counter which counts from upward direction like 0, 1, 2, 3 up to n. This is called as a counter. Down counter, a counter which counts in downward direction like n minus 3, n minus 2, 3, 2, 1, 0 in this fashion. Okay, so if you observe carefully, each count of the counter is called as state. This is a 0 state, the next this is a 1 state, this is a second state, this is a third state. It is each count of this counter is called as a state of the counter. The next, the number of states through which counter is passes before returning to original state is called as a modulus of counter. For example, suppose this is a 2-bit counter and it counts from 00, 01, 10, 11. Okay, and it again comes to the 00 conditions. So this counter is passes from 4 different states. This first state, second, third and fourth. So it is called as modulus of 4 counters. We will see one example. This example is here. Okay, for example, we are considering here a 2-bit counter we want to design a 2-bit counter. Then this counter consists 4 states. Which are those 4 states? Because of 2 bits, these 2 bits produces 4 different combinations. Okay, because number of values is equal to number of 2 raised to n, where n is nothing but number of bits. So 2 raised to 2 becomes 4, so it produces 4 different values, and those are 0 0, 0 1, 1 0 and 1 1. Hence this counter, 2-bit counter, is passes from 4 different level states. This is the first state, this is second state, third state and fourth state. So it is called as modulus of 4 counter. In the similar way, we will take another example, the example in which we are going to implement a 3-bit counters. Okay, so this 3-bit counter is passes through, that is number of values is equal to 2 raised to n, where n is equal to 3, because number of bits are 3, so it produces 8 different states, and these are 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. Hence this counter is passes from 8 different states, so it is called as modulus of 8 counter. Okay, the another way to find out number of states is nothing but 2 raised to n. Okay, what is the n? Number of bits. Suppose this is 2-bit counter, so it will be 2 raised to 2 becomes 4. This is produces 4 different states. Suppose this is 3-bit counter, it will produce 2 raised to 3, 8 different states. Okay, this is another approach in which we can easily find out the number of states. Next, number of flip-flops which are required for the implementation of modulus of n counters, which is represented for formula n is less than or equal to 2 raised to n, where n is nothing but number of flip-flops. Okay, for example, we need modulus of 16. So here n is equal to 16, and at which value of n this equation will be satisfied. So we will consider n is equal to 4. So 2 raised to, that is 16, is less than or equal to 2 raised to 4. So it will be gives you this value. So number of flip-flops are required is 4. In this way we can find out any value. For example, modulus of 32. So n is equal to 32. Okay, but we want to find out number of flip-flops, so we don't know n. So for example, we are know 32, at which value this equation will be satisfied. So we will first consider 4. N is equal to 4, that is 2 raised to 4 is equal to, it will be 2 into 2 into 2 into 2, it will be 2 into 2, 4, 4 into 2, 8, 8 into 2, 16. 16 is not equal to 32. So we will consider, we will increase one more flip-flop, it will be n is equal to, right now, 5. So 2 raised to 5, nothing but 2 into 2 into 2 into 2 into 2, 2 into 2, 4, 4 into 2, 8, 8 into 2, 16, 16 into 2, 32. So we required 5 number of flip-flops to count up to 32. I hope so you understand this is the basic information which are required for the counters. Let's start with the first point of counter is design and implementation of asynchronous counter. With the one more point of counter is the design of asynchronous counter. Okay, for the implementation of asynchronous counter, we are only using those flip-flops having the toggling characteristics. So as per our knowledge, we study SR, JK, T and D flip-flop. Apart from that, JK and T flip-flop are 2 flip-flops having characteristics like toggling conditions. That's why only these 2 flip-flops are used for the implementation of asynchronous counters. So these asynchronous counters can be implemented by using positive age triggered flip-flop, or another way, negative age triggered flip flop. Okay, but some points we have to study. First, if you want to implement asynchronous up counter, in that the complement output of first flip flop is acts as a clock to the second flip flop, and the complement output of second flip flop is acts as a clock to the third flip flop, and so on. This point to be considered because we are going to implement a positive age triggered asynchronous up counter. That's why complement output of first is acts as a clock to the next. For the implementation of asynchronous down counter in the same titled, that is positive age triggered flip flop, non-complement output of the first is and acts as a clock to the second flip flop. This minor change between the up counter and down counter. Okay. The another point, the asynchronous counter can be implemented with the help of negative age triggered flip flops. Okay. So in the implementation of up counter, we use non-complement output of first flip flop as an clock to the second one, and for the down counter, complement output of first flip flop acts as a clock to the second one. Okay, these small changes we have to take in considerations when we are going to implement or design a asynchronous counters. Okay, so the first part is that design a 2-bit up counter using positive age triggered JK flip flop. What we have to implement? 2-bit asynchronous up counter, and by using positive age triggered flip flops. Okay, so for the implementation of positive age triggered flip flops, and in that we are going to implement up counter, then we have to take consideration is that complement output of first flip flop is acts as a clock to the second one, and this another statement for the down counter, we have to use non-complement output as a clock to the second one. Okay, so according to that we can implement. First, this is a circuit diagram for the 2-bit up counter using positive age triggered, because this is a arrow shows this is a positive age triggered flip flops. Okay, because there is no bubble in front of this arrow. The flip flop is works as an toggling condition when j and k is equal to 1. When j and k is connected to the 1, which are studied into jk flip flops, which are studied into operation of jk flip flops. Okay, this is the operation. When j and k are 1, what is the output of present state is 0. Suppose it will be 0, then next state output is the complement of the present state, and vice versa. These considerations we have to take for the toggling conditions. Okay, so first, no doubt, as per toggling condition, j and k almost 1 connected to plus 5 volt or logic 1 value. Then suppose assume when there is no clock pulse is applied, then what is the contents? The both outputs of the flip flop are 0 0 when there is no clock pulses are applied. Hence q of 1 and q of 2 initial are 0 zeros. Okay, when first clock is applied, then what will be happen? This j and k are connected to logic 1. Definitely due to this toggling will be happen, and due to the previous state output is 0, next state will be 1. So this will be, this bit will becomes 1. Okay, if complement non-complement bit will be 1, then this will be 0. If this is 0 is applied, then this flip flop is not active on, so it will be remains off condition. So q of 2 will be in 0 value. Q of 2 will be in 0 value. So this bit is as it is, because flip flop 2 is not going to be on. When second clock is applied, now initial condition, what is the value of q is 1. Due to toggling condition, it will becomes to 0. Okay, if non-complement output is 0, then what will be complement output? It will be 1. And due to this, flip-flop 2 is on, and that's why this 0 is converted into 1 because of the toggling condition, because JA2 and K2 are connected to logic 1. So this will be 0 and this will be 1. When third clock is applied, then this again converted into 1 because of the toggling condition, and this is becomes 0, and no clock is applied to the second flip-flop. Hence flip-flop 2 is in the off condition and this bit as it is. So this is converted 0 to 1 and this 1 as it is. Okay, so that if you observe carefully, this is a 2-bit up counter which counts from 0 0, 0 1, 1 0 and 1 1. Hence it passes through 4 different conditions: 0, 1, 2 and 3. Hence it is called as a modulus of 4 counters. Okay, one more condition is that we are going to implement up counter by using positive edge triggered, so we have to use a complement output as an clock to the second flip-flop. Okay, let's take one more example. Okay, the example is that design 2-bit asynchronous down counter using ZK flip-flop. Use positive edge triggered logic operations. Okay, for the positive edge triggered logic operations, we have to implement down counter. So for the down counter, we have to use non-complement output as a clock to the next one. So whatever this Q1 will be acts as a clock to the second one. Okay, because both the flip-flops should be in the toggling condition. So J1 K1, J2 K2 are connected to plus 5 volt is nothing but logic 1 value. Okay, so initial condition we assume that there is no clock pulses are applied. Hence Q1 and Q2 both are in the 0 0 form. Okay, but when first clock is applied, this will be changed to initial, this is 0, it will be changed to 1, and this 1 is present here, and due to this flip-flop 2 should be on. That's why this Q2 initial will be 0 and it is also toggles to the 1. So both bits are 1 1. Okay, are you understand? First let me explain once again. When first clock is applied, initially what is the value of Q of 1? The value of Q of 1 is 0. Okay, what is the value of Q of 2 is also 0. When clock is applied and both the inputs are logic 1 value, so we are performing, this is the toggling condition. When clock is applied, these bits will be converted to 0 to, bits are changed to 0 to 1 as well as this 0 to 1. Hence when first clock is applied, both the conditions are output are 1 1. Okay, when second clock is applied, the initially this will be 1, this toggles to the 0. Due to this, no clock is applied to second flip-flop and second flip-flop is in the off condition. So this bit will be 0 and this will not going to be changed, so it is as it is 1. Okay, when third clock is applied, again this 0 is going to be changed for 1 because of toggling condition, which 1 is present here. Due to this, flip-flop 2 is active high, or you can say on state or set state. That's why Q of 2 will be changed from 1 to 0. So this is a 1 and this is a 0. So that if you observe carefully, and last one for the fourth clock, both the contents are 0 0. So that if you observe carefully, this flip-flop, this is a counter in which we starts the counter from 3 2 1 and 0. Hence this counter is called as a down counter. I hope so you understand little bit about 2-bit up counter and 2-bit down counter. Let's continue with the implementation or design of mode 6 asynchronous counter using T flip-flops. sorry, we are going to change something. Instead of modulus of 6, right now we are concerned with the design of modulus of 10 asynchronous counter using T flip-flop. It is very important point of discussion, because modulus of 10 counter is also referred as a decade counter, and it is also called as a BCD counter, because what is meaning of decade? Decade means tens, is consecutively counts the 10 values, so it is also called as decade counter. And BCD number, we know that 0 to 9 are the valid number of the BCD, so it is also called as a BCD counter. That's why we are consider this as an example point of view. So before going to start, we have to know that we are going to study modulus of 10, which counts from 0 to 9, and when 1010 is reaches, when all the contents of the flip-flop are 1010, then the counter or flip-flops are automatically resets. That's why we want to design such kind of logic. So Q4, Q of 3, Q of 2, Q of 1. 1010 is nothing but 10. Okay. When this value is reaches by this counter, then automatically all bits of all outputs of these flip-flops are 0 or reset condition. So that we provide here one output is called input is called as clear complement. Okay. When this is an active low signal, then this, due to this complement, this is produces clear signal, which is resets all the flip-flops, and the contents of all the flip-flops are going to be 0 0 0 0 when the counter reaches to 1010 count. That's why we use a NAND gate between the Q of 2 and Q of 4, because these two bits are only 1. So this 1 into 1 becomes 0, and this 0 is comes here, and 0 complement is becomes 1. That's why all the contents of flip-flop are going to be reset, or it going to be 0. So when there is no clock pulse, all the contents of the flip-flop are 0 0 0. Okay, we are using T flip-flop, and we have to use we are going to use negative edge triggered flip-flops. So if you want to implement modulus of 10, we have to count from 0 1 2 3 4 5 6 7 8 9 10 onwards. If you observe carefully, this counting is in upward direction. So this is negative edge triggered, and we need a up counter. That's why there is a one point asynchronous up counter by using negative edge triggered, in which non-complement output of each flip-flop is acts as a clock to the second one, or so on, so that whatever non-complement output of each and every flip-flop is acts as a clock to the next flip-flops. So at initial condition, we are going to assume the clock, there is no clock, so contents of all the flip-flops are 0 0 0. So when first clock is applied, definitely this is a toggling condition. This initial value is 0. Due to toggling, it will be going to be changed, it will be 1. Okay, due to this 1 is given to bubble, so it will be converted into 0. So flip-flop 2, flip-flop 3 and flip-flop 4 are in the off state. So the contents of output of all the flip-flops are not going to be changed. When a second clock is applied, then what will be happen? This bit going to be changed or toggles, it will be 0. Okay, due to this 0, it converted into logic 1 due to negative is triggered, and that's why this flip-flop is in the set condition. So initially this Q of 2 is 0, and due to flip-flop is on, this 0 is toggles to the 1. So this is a 0, this will be 1. If this is a 1, then due to this bubble, this converted into 0, and that's why flip-flop 3 and flip-flop 4 are in the reset condition, so output is not going to be changed. So for third clock, again for third clock, what will be happen? This will be changed to 1, because toggling condition, it will be once. Okay, this 1 is going to be appear here. Due to negative state order, it will be 0, and flip flop 2 is not going to be change their state, which is as it is. This is a 1, this is a negative state order, so flip flop 3 and flip flop 4 are in the reset condition, which is value is 0 0. Next, for the fourth clock, when fourth clock is applied, this bit going to be changed, it will be 0. Okay, due to this 0 will be appear here, the 0 is converted to 1. That's why flip flop 2 is set condition, or you can say on. That's why this 1 is converted to 0. Again, the 0 is present here, which is inverted 1, and due to this flip flop 3 is set, and this initial bit is 0, it will be changed to 1. So the contents are 0 and this will be 1. Okay, this 1 is inverted here, and due to this flip flop 4 is again in the reset condition, and it will be 0. Next, when fifth clock is applied, definitely this bit is going to be toggle, it will be again 1. Okay, due to this 1, this flip flop is again reset, because this 1 is converted into 0 because this of bubble. So this is a reset flip flop, so no output will be going to be changed. Again, this will be as it is, so this is again 1, and this is not going to be changed, this is also 0. Okay, then for the next sixth clock, for the sixth clock, this will be toggled to 0. Due to this 0, this present here, this due to this bubble, it will be going to be changed for the 1. Due to this, the flip flop will be set, and this will be 1, because this 0 is toggling to 1. If this 1 is present here, then this is again 0, and hence flip flop 3 is again in the reset condition, so no output is going to be changed, so which is as it is. And due to this 1 is present here, which is 0, and due to this flip flop 4 is again in the reset condition. For the 7, again the same count, it will be 0 1 1 1. For the 8, what will happen? 1 for the 8, this will be 1, this is also 1, this is also 1. Okay, when first 8 number clock is applied, then this will be 0, it toggles to the 0. Okay, the 0 is applied here, which is 1. Due to this flip flop 2 is set, this again toggles to the 0. This 0 is applied here, which is converted into 1. Again flip flop 3 is toggles it to the 0, and this will be 0 is going here, and due to this it will be makes a flip flop on, because due to this bubble, and flip flop 4 will be on, and remaining all flip flops are 0 0. Okay, then next condition, that is 9. No need to explain this 9th condition. I hope so you understand what happens when 9th clock is applied. The contents are 1 0 0 1, and it is very interesting to see about what happens when 10th clock is applied. If you observe carefully, when 10th clock is applied, the contents of this flip flop are, I will write here separately. This will be 1, this is a 0, this is a 1, and this is a 0. Okay, this 1 is present here, and this is 1 is also present here. 1 into 1, it becomes 0, and this 0 is present here, and 0 complement it will be 1. This is also 1, this is also 1, and this is also 1. That means that when the counter reaches to 1 0 1 0 combination, at that time, due to this logic circuitry, all the flip flops are in the reset condition due to this clear complement signals, and the flip flop contents are 0 0 0 0. If you observe carefully, the working operation of this flip flop, which counts from the 0 1 2 3 4 5 6 7 8 9, so it is called as a decade 10 counter. I hope so you understand very easily design of modulus of 10, or sometimes decade counter or BCD counter very nicely. Thank you very much.